Now I want to talk about a very important article which is called Dual Decomposition with Many Overlapping Components. And it is written in 2011. And there's very similar articles like this one and this one that their ideas are similar. So the problem of structure prediction, let's recall this problem that so we assume to have a model that assigns a score to each candidate output based on which we predict the maximum score. And why is a structure like dependency parsing, words are related to each other, or like argument mining, argument frameworks that it's again like a graph, but now sentences are related to each other. For example, some of them support each other or are against them. So the problem of dual decomposition is not new. It goes back to many years ago in 1990 or even before that. So you can always decompose, and also you have seen this in the literature for optimization that you see that they decompose into some blocks. For example, Z1 is some block and Z2. So Z1 are these entries and Z2 are these entries. So it's also a paradigm in distributed optimization because you want to make everything parallel, do parallel computing. So all distributed computing, all distributed optimization is all about this. And also it goes back to the work of Danzig, Wolfert. This is another approach, another application. That, for example, you want to solve the linear programming or integer linear programming, and you write everything in terms of linear combination of these corners. And now because you have a linear combination, you can create some blocks so that these blocks are decoupled, and you can do lots of interesting things and solve each of them separately in parallel, so it's very efficient. And there are other articles like this one that talks about decomposition or factored MDPs. And so the assumptions that we use in this paper, because this is the application of decomposition for example, dependency parsing. So we assume that we have some basic parts, and basic parts in this paper are just arcs. We are not talking about higher order relations like siblings and grandparents, and so when we're talking about these basic parts, we mean these arcs. And we assume that only basic parts overlaps, and arcs are the basic parts. So we can have different higher order relations like consecutive siblings, grandparent, or all siblings and all of them. So how can we combine these information? Well, the basic idea is like this. So look at V as some factors, or let's say constraints. For example, one factor, one ZS, for example, Z2 is like this, that it says that it combines two arcs and make a constraint just by combining these two arcs, or any other arcs that has valuable syntactic or semantic information. And so in this example here, you see that all of ZS, for example, we have ZR, we have R constraints, and these are just these are the arcs, simple arcs that we use. And a combination of those arcs, if we use the combination of those arcs, it means that we are going to the higher order features, not just simple arcs that all first order parsing is all about. Now we're going to higher order parsing. It's much more difficult, and so we maximize this summation of all the scores of all of these, because they are additive, and they're subject to, first of all, they should satisfy these constraints, and this makes everything we cannot fully decentralize them. That's why we have a master here and some slaves, and these slaves that be computed on different computers over the cloud. These slaves, slave 1, slave 2, slave 3, slave 4, they talk to the master, they collaborate, they send information to make sure that all of them are consistent with each other. And so the primal problem, we want to relax the primal problem. So this is the relaxed version of the primal problem, by saying that, okay, Z can be in Z of S, and still this should satisfy. But in the dual version, we use the Lagrangian, and the Lagrangian variables become your dual variables and those things. But what is interesting is that we can write the master, this interacts with the slaves, and the slaves are these, the solution of these. But each of them is a separate. For example, when S is 1, we have a different slave. When S is 2, we have a different slave. And all of these slaves, they send messages to the master, and they talk to each other in order to send information. And it is shown here, they are talking to each other, and we will solve it using ADMM, for example. And this is the way that takes an average of the information that are inside each of these slaves. They combine this information. It's like saying that I know there are different ideas in this room, but we can take a kind of average that has common things to all of the ideas of people in this class. So it takes the most common approach that has the least variance to other ideas. So here we are taking, and so of course I forgot to say that this Z, I should say simple example. For example, Z of S of R, when R is equal to 3, it means that the S constraint, when it talks to the relation to the third arc, if it is 1, it means that it's connected. If it is 0, it is not connected. And we combine these information. And here are the update for the Lagrange variables, that you will see lambda inside the here. This lambda is inside the problem of slaves. So you may say, how these slaves interact with the master? I would say this is lambda. This is the way that they interact with each other. And T here, it refers to time, because at each iterations we have different lambda, different U, and everything changes, and all of these and this is a quadratic, by the way. This is a quadratic, integer quadratic, let's say mixed integer quadratic programming. This is quadratic because of this residual term that in the literature of optimization they call it augmented Lagrangian, because it has some nice advantages, although it adds a nonlinearity, but it has good properties. And the prime one, and you may say we don't run our algorithm forever, and that's why we have some residual, primal residual and dual residual that says, okay, if they're after a threshold, then we are good, we're done, and we can just publish our result. And solving the sub-problems, you know that these integer quadratic problem becomes very expensive, but if the number of variables are not big, then you can find even an explicit closed form solution. For example, pairwise factors is a special case, existential quantification for a different problem, Markov logic networks or different problems. You can have a simplified closed form solution, and that's why you reduce the complexity of that very, very complex quadratic optimization problem. And you see, for example, for different, for siblings, we have order of n cubed number of slaves. So the number of slaves grows. And these are the results that you see. The Chinese one is a little bit, I expect to be lower, but the Turkish one is more difficult. And so the Turkish one, we should improve the state of the art for the Turkish language. And you see ADMM full is better than subgradient full that those researchers in Japan have used. And we can, with very few iterations, we can get a very high accuracy just with very few iterations if we use, for example, this blue one, which is ADMM full, in contrast to subgradient full, which performs badly here. And so the rate of convergence for ADMM full, as you see, is very, very sharp, and it is much faster.